Hello there. I'm so glad you found your way here tonight. Wherever you are in the world right now, allow yourself to settle into this shared moment of stillness. Let the noise of the day fade away. Let your thoughts grow quiet, like the soft glow of distant stars emerging one by one as twilight deepens. Right now, as you listen to these words, the night sky stretches endlessly above you. A vast canvas of darkness scattered with ancient lights. Some of those points of brightness are stars already gone, their final glow still traveling toward us across the void. Others are galaxies so distant that their light began its journey before life even existed on Earth. Tonight we look upward into the quiet wonder of the night sky. A place of eclipses and auroras, of wandering planets and meteor showers, of constellations that have guided travelers for thousands of years. We will explore how starlight bends through our atmosphere, how the moon shapes our tides, and how galaxies beyond counting hide in what looks like empty darkness. We will discover pulsars spinning faster than thought, comets returning after centuries, and the faint glow of creation itself still warming the cosmos. All of it waiting to be shared in the stillness. Tonight, let's drift off together while exploring over 100 soothing facts about the night sky. There's no rush here. No test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the stars and wonders above. Either way, this space is for you. There is something deeply calming about contemplating the night sky. Every star carries the memory of cosmic furnaces burning for billions of years. Every constellation holds stories told by generations stretching back to the dawn of civilization. You are connected to this story more than you might realize. The atoms in your body were forged inside stars that lived and died long before our sun was born. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it came from the hearts of ancient suns scattered across the galaxy. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow, and let the weight of the day drift away like clouds parting to reveal the stars beyond. The night sky is patient beyond measure. Stars burn for billions of years before fading. Light crosses unimaginable distances before reaching our eyes. Constellations shift so slowly that 100 human lifetimes would barely notice the change. And yet, within all that steadiness, there are sudden bursts of wonder. Shooting stars blazing across the darkness, eclipses that turn day into twilight, auroras dancing like curtains of colored light. Tonight we will wander through this magnificent celestial world. We will meet the familiar lights of planets and stars, and discover hidden wonders that only reveal themselves to patient eyes. But there is no hurry. The universe has been here for nearly 14 billion years. It can wait a little longer while you rest. Let us begin with the stars themselves. Every star visible to your naked eye belongs to our own galaxy. When you step outside on a clear night and gaze upward at the scattered points of light, every single one of them resides within the Milky Way, our home galaxy. The nearest star beyond our Sun, Proxima Centauri, lies roughly 4 light-years away, yet even at that immense distance, it belongs to the same galactic neighborhood. The most distant stars visible without optical aid are several thousand light-years from Earth, still well within the 100,000 light-year span of our spiral galaxy. Although the universe contains trillions of galaxies, each brimming with billions of suns, none of those external stars can be seen individually from our vantage point. The light they emit is simply too faint to register on the human retina without the help of telescopes. Every sparkle you see is a member of the Milky Way, a fellow traveler circling the galactic center alongside our own sun. This shared cosmic citizenship connects every point of light in our sky. The Andromeda Galaxy, visible as a faint smudge, is the only external galaxy most people can see unaided, yet even then we perceive the combined glow of its billions of stars, rather than any single sun. Some stars you see tonight may have already died long ago. Light travels at a fixed speed, roughly 300,000 kilometers every second, yet even at that pace it requires years, decades or centuries to cross the gulf between distant stars and our eyes. When you observe a star situated 500 light-years away, you are witnessing it as it appeared 5 centuries in the past. If that star exhausted its fuel and collapsed in the meantime, the news of its demise has not yet reached us. Massive stars burn through their reserves quickly and can explode as supernovae within a few million years, a blink in cosmic terms. Some of the familiar points of light in our constellations may already have vanished, their final brilliance still racing toward us across the void. This delay means the night sky is not a live broadcast, but a mosaic of different eras, each star frozen at the moment its light departed. Looking up is quite literally looking back in time. The cosmic time lag creates a continuously updating archive, where new information arrives constantly, as old light completes journeys that began before recorded history. Polaris has not always been our guiding North Star. The Earth wobbles slowly on its axis like a spinning top, a motion called precession that takes roughly 26,000 years to complete one full cycle. As a result, the point in the sky around which everything appears to rotate shifts gradually over millennia. Polaris currently sits nearly at the celestial North Pole, making it a convenient reference for navigators, but this was not always the case. Thousands of years ago, the star Thuban in the constellation Draco held that position, guiding ancient Egyptian pyramid builders. In another 12,000 years, the bright star Vega will assume the role of the northern pole star. The sequence continues endlessly, cycling through different stars as Earth's axis traces a great circle across the heavens. This cosmic wobble reminds us that even constants we take for granted are subject to the slow rhythms of celestial mechanics. The North Star is a temporary title passed from one luminary to the next. Ancient travelers navigated oceans and deserts using the stars above. Long before compasses and satellites, mariners and desert caravans relied on the fixed patterns of stars to find their way across featureless expanses. Polynesian voyagers crossed vast stretches of the Pacific Ocean by memorizing star paths and the rising points of specific constellations. Arab traders crossing the Sahara tracked their progress by observing the altitude of Polaris and the positions of familiar asterisms. In the Mediterranean, Greek and Phoenician sailors used the Big Dipper and the Southern Cross to determine latitude and maintain course. This celestial navigation demanded intimate knowledge passed down through generations, an oral tradition of sky maps that predates written records. The stars offered a reliable guide because their patterns remain consistent night after night, year after year. Even today, astronauts and emergency navigators learn the fundamentals of star navigation as a backup to electronic systems. The night sky was humanity's first GPS. Instruments like the astrolabe and the sextant refined these ancient techniques, transforming stargazing into precise positional science that charted new continents and opened global trade routes. The Milky Way appears as a hazy band because we are inside it. Our solar system resides within one of the spiral arms of a vast, disc-shaped galaxy, spanning roughly 100,000 light-years. When we look toward the galactic plane, we peer through the combined glow of billions of distant stars packed too closely together for our eyes to resolve individually. This blended light creates the soft milky ribbon arching across dark summer and winter skies. When we gaze perpendicular to the disk, we see fewer stars and more empty darkness because we are looking out of the galaxy rather than through it. Ancient cultures gave the Milky Way many names and wove it into origin myths, seeing it as a river, a road, or spilled milk from the heavens. Modern astronomy confirmed that this luminous streak is our edge-on view of our own galactic home. The haze is not distant fog, but the collective glow of suns beyond counting. Our galaxy contains hundreds of billions of stars beyond what we can see. Even on the clearest, darkest night, the unaided eye can perceive only a few thousand stars at most. Yet current estimates suggest the Milky Way harbors between 100 billion and 400 billion suns, the vast majority far too faint or hidden by interstellar dust to reach our retinas. Many lie on the opposite side of the galactic center, blocked by clouds of gas and dense star fields. Others are small, dim red dwarfs that emit only a fraction of the light our sun produces. Telescopes and infrared detectors have revealed countless stars invisible to human sight, mapping populations that would otherwise remain unknown. The galaxy is far richer and more crowded than naked eye observation suggests. For every pinpoint you count on a clear night, there are millions more sharing the same cosmic neighborhood, glowing unseen but nonetheless present. The combined mass of these hidden suns shapes the gravitational dynamics of the Milky Way, influencing everything from the orbits of nearby stars to the long-term fate of the galaxy itself. Shooting stars are not stars at all, but tiny grains of cosmic dust. The streaks of light we call shooting stars are actually caused by minuscule particles, often no larger than grains of sand, burning up as they plunge into Earth's atmosphere at tremendous speeds. These particles originate from comets and asteroids that shed debris along their orbits around the Sun. When our planet crosses one of these dusty trails, the particles collide with atmospheric molecules and generate intense friction, heating to incandescence and leaving glowing trails across the sky. Most of these meteors vaporize completely long before reaching the ground. The brightest events, called fireballs or bolides, may involve fragments the size of pebbles or larger. Despite their celestial appearance, shooting stars are visitors from our own solar system, rather than distant suns. Their fleeting brilliance is the final moment of a journey that may have lasted millions of years drifting through interplanetary space. The colors of meteor trails depend on the chemical composition of the particle, with magnesium producing blue-green hues and sodium lending an orange glow. From the darkest places on Earth, thousands more stars become visible. In remote locations far from artificial lighting, the night sky transforms into a tapestry of astonishing richness. Under truly dark conditions, a careful observer can see between 2,000 and 3,000 stars with the unaided eye at any given moment. Add the other hemisphere's stars visible from different latitudes, and the total rises to roughly 6,000. This abundance is dramatically diminished in urban areas, where sky glow washes out all but the brightest objects. Dark sky preserves and remote deserts offer glimpses of what our ancestors saw every night before electric lighting reshaped our relationship with the heavens. In these sanctuaries, the Milky Way blazes overhead like a luminous river, and faint nebulae become visible to patient eyes. Experiencing a pristine sky reminds us how much of the cosmos we normally miss. Darkness reveals the universe in its full splendor. The Bortle scale ranks sky darkness from 1 to 9, with Class 1 representing the most untouched wilderness skies where even the zodiacal light and airglow become apparent. Light pollution has erased the Milky Way from many urban skies. Over the past century, the spread of artificial lighting has fundamentally altered our view of the heavens. Studies suggest that a significant portion of the world's population lives under skies too bright to reveal the Milky Way at all. Streetlights, advertising signs, and illuminated buildings scatter light into the atmosphere, creating a perpetual glow that drowns out faint celestial objects. This pollution not only affects stargazers, but also disrupts nocturnal wildlife and human circadian rhythms. Organizations around the globe now advocate for responsible lighting practices that direct illumination downward and reduce unnecessary brightness. Dark sky parks have been established to protect the remaining pockets of natural darkness. Reclaiming the night sky requires awareness and collective effort. The stars have not faded, we have simply surrounded ourselves with too much competing light. Cities are beginning to adopt shielded fixtures and warmer-colored bulbs that reduce sky glow while maintaining safety and visibility on the ground. Constellations slowly change shape over thousands of years. Stars are not fixed in place, but travel through the galaxy along their own orbits, each with a slightly different speed and direction. This movement, called proper motion, is imperceptible on human timescales, but accumulates over millennia. Given enough time, the familiar patterns we call constellations will distort and eventually become unrecognizable. The Big Dipper, for example, looked quite different 100,000 years ago, and will morph into a new arrangement 100,000 years hence. High-velocity stars move faster than most, visibly shifting position over centuries when measured with precision instruments. The constellations are not eternal fixtures, but snapshots of a constantly evolving stellar ballet. Every generation inherits a sky slightly altered from the one before. The heavens are in perpetual motion, though the timescale far exceeds our brief lives. Astronomers can simulate these changes using computer models, reconstructing the past and predicting the future shapes of familiar asterisms over millions of years. The southern hemisphere reveals entirely different constellations. Because Earth is a sphere, observers in the northern and southern hemispheres gaze upon largely separate swathes of the celestial sphere. Those living in Australia, South America, or Southern Africa can see constellations invisible from most of Europe and North America, including Crux, the Southern Cross, Centaurus, and the brilliant stars of Carina. Similarly, far northern constellations like Ursa Major and Cassiopeia never rise above southern horizons. Only the region around the celestial equator is visible from both hemispheres. Travelers crossing from one hemisphere to the other often describe the experience of encountering an entirely unfamiliar sky. The Magellanic Clouds, satellite galaxies of the Milky Way, are a southern treasure invisible to most northern observers. This division of the sky underscores how location on our planet shapes our cosmic perspective. The universe offers different wonders depending on where you stand. Indigenous traditions in the southern hemisphere developed rich sky lore around these unique constellations, weaving stories that have survived for tens of thousands of years. The Andromeda Galaxy is faintly visible without a telescope. Under dark skies and away from light pollution, The Andromeda Galaxy appears as a faint smudge of light in the constellation of the same name. It is the most distant object regularly visible to the unaided human eye, lying roughly 2.5 million light-years from Earth. Despite its distance, Andromeda spans several degrees of sky, wider than the full moon, though most of its extent is too dim to see without optical aid. Ancient observers noted this fuzzy patch, and catalogued it long before telescopes revealed its true nature as a spiral galaxy containing 1 trillion stars. Andromeda is on a slow collision course with the Milky Way, destined to merge with our galaxy in several billion years. For now, it hangs in our autumn and winter skies as a reminder of the universe beyond our own stellar neighborhood. Viewing it is seeing light that left its source before humans walked the Earth. Light from Andromeda began its journey more than 2 million years ago. When the photons now entering your eyes departed Andromeda, early hominids were just beginning to walk upright on the African savanna. The entire span of recorded human history fits within a tiny fraction of that journey. This cosmic time lag means we never see Andromeda as it exists right now, but only as it appeared in the distant past. Any events occurring there today, whether new stars igniting or ancient ones dying, remain unknown to us until their light completes the long crossing. The same principle applies to every distant object in the sky. The further away something is, the deeper into history we peer when we observe it. Andromeda's light is a messenger from an epoch before our species existed. Gazing at it connects us to a past so remote that our entire civilization is but a heartbeat in comparison. The photons that reach your eyes have witnessed nothing during their voyage, yet they carry encoded information about conditions that prevailed in a galaxy far removed from our own. Some stars recorded by ancient astronomers no longer exist today. Historical records from civilizations across the globe describe brilliant guest stars that appeared suddenly and then faded from view. Many of these events were supernovae, the catastrophic explosions that mark the death of massive stars. Chinese, Arab, and medieval European astronomers documented such transient lights in careful detail. In several cases, the stars that exploded have long since vanished, leaving behind only expanding remnants of gas and neutron star cores. The star that produced the Crab Nebula, observed widely in the year 1054, no longer shines in the traditional sense. It exists now as a rapidly spinning pulsar. These ancient observations are invaluable to modern astronomers seeking to understand stellar evolution. They remind us that the sky is not static, but a theater of ongoing change. The records of stargazers centuries ago captured moments of cosmic drama. A star's color reveals its temperature and energy. The hues of stars range from deep red to blazing blue-white, and this variation corresponds directly to their surface temperatures. Cooler stars glow red or orange because they emit the bulk of their energy at longer wavelengths. Hotter stars radiate at shorter wavelengths, shifting their light toward blue and white. Our Sun, with a surface temperature of around 5,500 degrees Celsius, appears yellow-white. Stars like Rigel in Orion blaze blue because their surfaces exceed 10,000 degrees. Betelgeuse glows red-orange at a comparatively cool 3,500 degrees. Astronomers use color and spectral analysis to classify stars into categories and determine their physical properties. Simply by noting the tint of starlight, an observer gains insight into the energy each sun pours into the cosmos. The night sky is painted in hues of fire and ice. These colors also hint at a star's age and stage of evolution, with blue giants burning furiously through their fuel while red dwarfs conserve energy across trillions of years. Stars appear to twinkle because of Earth's restless atmosphere. The shimmering quality of starlight, so often celebrated in poetry and song, arises not from the stars themselves, but from turbulent air high above our heads. As light passes through layers of atmosphere moving at different temperatures and densities, its path is bent and refracted in constantly shifting ways. This causes the star's image to dance and flicker, producing the familiar effect of twinkling. Planets, which appear as tiny disks rather than points, twinkle less, because the disturbances average out across their larger angular size. On calm nights or from high-altitude observatories, twinkling diminishes significantly. Astronomers often prefer mountaintop sites where the air is thinner and steadier. For casual stargazers, the twinkle adds charm to the night sky, but it is fundamentally an atmospheric illusion rather than a property of stellar light. Adaptive optics technology now allows ground-based telescopes to counteract atmospheric distortion in real time, producing images nearly as sharp as those taken from space. In space, stars shine with perfect steady clarity. Above Earth's blanket of air, stars do not twinkle. Astronauts aboard the International Space Station and instruments on space telescopes observe stars as unwavering points of light. The absence of atmospheric distortion allows for sharper images and more precise measurements than any ground-based observatory can achieve. This clarity is one reason orbital telescopes like Hubble have revolutionized our understanding of the cosmos. Without the shimmer of refracting air, features invisible from Earth become discernible. The stark difference between ground-based and space-based views underscores how much our atmosphere influences what we see. For billions of years, every creature on this planet has viewed the universe through a veil of air. Escaping that veil reveals the cosmos in crisp detail, as if cleaning a dusty window for the first time. The steady starlight observed from orbit has enabled precise measurements of stellar distances, and the discovery of exoplanets through subtle brightness variations. Some massive stars fuse heavier elements deep within their cores. In the hearts of the most luminous stars, temperatures and pressures rise so high that nuclear fusion climbs beyond hydrogen and helium. These stellar furnaces forge carbon, oxygen, neon, silicon, and eventually iron, building up layers like an onion. Each new element requires higher temperatures to ignite, and the process accelerates as the star nears the end of its life. Iron marks the final stage because fusing it absorbs rather than releases energy, robbing the core of the support it needs to resist gravity. When the core collapses, the resulting supernova scatters these heavy elements into space, seeding future generations of stars and planets. Without this cosmic alchemy, the calcium in our bones, the iron in our blood, and the oxygen in our lungs would not exist. Massive stars are the forges of the periodic table. Elements heavier than iron are synthesized in the intense conditions of the explosion itself, or in neutron star mergers, distributing gold, platinum, and uranium throughout the galaxy. Sirius is the brightest star visible in our night sky. Dominating the winter skies of the northern hemisphere and the summer skies of the southern, Sirius blazes with a brilliance that outshines every other star. Its luminosity results from a combination of factors. It is relatively close to Earth at just under 9 light-years, and it is intrinsically more luminous than our Sun, radiating roughly 25 times as much energy. Sirius formed part of the constellation Canis Major, earning the nickname Dog Star. Ancient astronomers across many cultures noted its rising in conjunction with significant seasonal events. In Egypt, its appearance heralded the annual flooding of the Nile. Sirius is actually a binary system, with a faint white dwarf companion orbiting the bright primary. This companion was one of the first white dwarfs ever identified. The star's brilliance marks it out as a beacon impossible to miss on clear nights. Sirius has inspired myths and legends across nearly every culture. From ancient Egypt to Greece, from the plains of North America to the islands of Polynesia, civilizations have woven stories around this unmistakable star. The Egyptians connected its annual rising with fertility and renewal, associating it with the goddess Isis. Greek and Roman writers linked its appearance with the hottest days of summer, coining the term dog days still used today. Indigenous Australian cultures incorporated Sirius into dreaming stories that explained the movements of seasons and the behavior of wildlife. Navigators of the Pacific used it as a waypoint in their voyages across vast ocean distances. Its prominence ensured that wherever humans looked up, Sirius demanded attention and explanation. This single point of light bridges continents and millennia, uniting diverse peoples through shared wonder. The Pleiades cluster sparkles like a tiny family of stars. Often called the Seven Sisters, the Pleiades are a compact group of young blue stars, nestled within a faint veil of nebulosity. To the unaided eye, 6 or 7 stars are easily visible, though binoculars reveal dozens more spread across the surrounding region. The cluster lies roughly 400 light-years away, and is one of the nearest open clusters to Earth. Its stars form together from the same molecular cloud, and are estimated to be around 100 million years old, mere infants on the cosmic scale. Cultures around the world have noted the Pleiades for millennia, incorporating the cluster into agricultural calendars and mythology. Ancient Greeks named the stars after the daughters of Atlas, weaving tales of pursuit and transformation. The Pleiades remain a charming target for casual stargazers, seeking beauty in a small patch of sky. Japanese tradition calls them Subaru, a name now famous as an automobile brand, whose logo depicts the cluster's brightest members. The Orion Nebula glows faintly within the Hunter's Sword. Hanging beneath the 3 bright stars of Orion's belt lies a region of celestial splendor, visible to the naked eye as a fuzzy smudge. This is the Orion Nebula, a vast cloud of gas and dust roughly 1,300 light-years distant. It serves as a stellar nursery, where new suns are being born from gravitational collapse even now. The glow we see is ionized hydrogen, energized by the fierce radiation of young hot stars embedded within the cloud. Binoculars reveal a distinct greenish tint, while telescopes unveil intricate structures of sculpted gas and dark lanes of dust. The nebula has captivated observers for centuries and appears in many catalogues of celestial wonders. It remains one of the most studied objects in all of astronomy. Orion's sword hides a forge of future solar systems. Infrared observations have revealed hundreds of protostars embedded within the nebula, many surrounded by disks of material that may one day form planets. Some nebulae shine because nearby stars energize their gases. Emission nebulae glow with their own light, rather than simply reflecting starlight from elsewhere. Intense ultraviolet radiation from young hot stars embedded within the clouds strips electrons from hydrogen and other atoms. When these electrons recombine with their atoms, they release photons at specific wavelengths, producing the characteristic reds, greens and blues we observe. The Orion Nebula and the Lagoon Nebula are classic examples. Their brilliant colors are testament to the energetic processes occurring within. These regions are often sites of active star formation, where gravity compresses gas until new suns ignite. The colors are not merely aesthetic, they reveal the chemical composition and physical conditions of the cloud. Emission nebulae are among the most photographed objects in the cosmos. They demonstrate how stellar radiation can transform cold, dark gas into luminous works of art. Other nebulae glow only by reflecting starlight like cosmic mirrors. Reflection nebulae do not emit light of their own. Instead, they scatter the light of nearby stars, much as fog scatters the headlights of a car. Dust grains within these clouds are often more effective at scattering blue wavelengths, giving reflection nebulae their characteristic bluish tint. The famous nebula surrounding the Pleiades is a prime example, its delicate haze visible in long-exposure photographs. Unlike emission nebulae, reflection nebulae are cooler and lack the energetic stars needed to ionize their gas. They often appear alongside emission regions, painting complex tapestries of red and blue across deep sky images. Observing them requires dark skies and patience, as their surface brightness is typically low. These cosmic mirrors transform cold interstellar dust into gentle glows of borrowed starlight. Many stars travel through the cosmos in pairs orbiting each other. Binary star systems consist of two stars gravitationally bound to one another, circling a common center of mass. These pairings can be as tight as a few solar diameters, or as wide as thousands of astronomical units. Some binaries are so close that material flows from one star to the other, creating violent outbursts visible across great distances. Others are visual doubles easily split with a small telescope, offering charming targets for amateur astronomers. The dynamics of binary systems have provided essential information about stellar masses and evolution. By watching how quickly two stars orbit each other, astronomers can calculate their combined mass with high precision. Binary systems have revealed that stellar solitude like our Sun's is actually less common than partnership. The night sky holds countless dancing duos, hidden among the solitary points of light. Some eclipsing binaries dim periodically as one star passes in front of the other, providing valuable data about stellar sizes and temperatures. Binary star systems may outnumber solitary suns like ours. Surveys of nearby stars suggest that single-star systems like our own may be the minority rather than the norm. When low-mass red dwarfs are included in the count, the balance shifts somewhat towards singles, but among Sun-like and more massive stars, binaries and higher multiples dominate. This prevalence has implications for planet formation. Gravitational interactions in multiple star systems can destabilize orbits, making habitable worlds less likely. Yet exoplanets have been found in binary systems, orbiting one star or circling both at a safe distance. The question of how common stable planetary conditions are remains an active area of research. Understanding binary frequency helps astronomers estimate how many suns in the galaxy might host planets like Earth. Our solitary sun may be the exception rather than the rule. The formation of binaries is tied to the dynamics of collapsing gas clouds, where fragmentation can produce two or more stellar embryos that remain gravitationally linked. Some systems contain 3 or even 4 stars bound together. Beyond simple binaries, the cosmos hosts hierarchical systems where multiple stars orbit in nested configurations. A common arrangement involves a close binary pair with a distant third companion circling far outside. In even more complex cases, 2 binaries orbit one another, creating a quadruple system. These arrangements remain stable because the stars are grouped at vastly different separations, avoiding gravitational chaos. The most famous example may be Alpha Centauri, our nearest stellar neighbor, which comprises 3 stars, a close binary, and a distant red dwarf. Such systems challenge traditional pictures of planetary formation, yet still occasionally harbor worlds. Observing the intricate orbital dances of triple and quadruple systems reveals gravity's capacity for elegant choreography. The night sky hides layers of complexity within what appears as a single point of light. Polaris, the current North Star, is itself part of a triple system, with two fainter companions orbiting the bright primary that guides navigators. Cepheid variable stars pulse rhythmically like cosmic heartbeats. Cepheid variables are luminous giant and supergiant stars that expand and contract in regular cycles, causing their brightness to rise and fall predictably. The pulsation periods range from a few days to several weeks, and are directly related to the star's intrinsic luminosity. Astronomers discovered this relationship in the early 20th century and immediately recognized its power as a cosmic yardstick. By measuring how long a cepheid takes to pulse, one can determine how bright it truly is. Comparing this to its apparent brightness yields the distance. Cepheids were instrumental in proving that other galaxies exist beyond the Milky Way. The star Delta Cephei in the northern sky gave the class its name. These rhythmic beacons continue to help calibrate the scale of the universe. The pulsation arises from the ionization of helium in the star's outer layers, which traps and releases energy in a self-sustaining cycle that drives the expansion and contraction. These pulsing stars helped reveal the true scale of the universe. In the 1920s, astronomer Edwin Hubble used Cepheid variables in the Andromeda Nebula to prove it was a separate galaxy far beyond the Milky Way. Before this discovery, many scientists believed the Milky Way constituted the entire cosmos. The precise relationship between a Cepheid's pulsation period and its luminosity allowed Hubble to calculate a distance that dwarfed anything previously imagined. This single insight transformed astronomy, revealing that the universe contained not one galaxy, but countless billions. Further observations with Cepheids established distances to galaxies ever further away, sketching the scaffolding of cosmic structure. These pulsating stars remain standard candles today, refined and recalibrated by successive generations of telescopes. They are the tape measures with which astronomers chart the immensity of space. Cepheids observed by the Hubble and James Webb Space Telescopes continue to refine our understanding of the universe's expansion rate, a value central to modern cosmology. Some dying stars swell into red supergiants, hundreds of times larger than the Sun. As massive stars exhaust the hydrogen in their cores, they begin fusing helium and heavier elements. This process releases energy that pushes the outer layers outward, causing the star to expand dramatically and cool at the surface. The result is a red supergiant, a bloated giant glowing with a deep crimson hue. If placed at the center of our solar system, some of these behemoths would engulf Mercury, Venus, Earth, Mars, and even Jupiter. Despite their enormous size, red supergiants are relatively short-lived, existing in this phase for only a few 100,000 years before collapsing and exploding. Betelgeuse and Antares are among the most famous examples, easily visible to the naked eye. These inflated stars are cosmic reminders that even suns have life cycles ending in dramatic transformations. The tenuous outer layers of red supergiants are so diffuse that they approach the density of a laboratory vacuum, yet they still glow with the combined light of tens of thousands of suns. Betelgeuse in Orion is nearing the end of its stellar life. This red supergiant marks the right shoulder of Orion the Hunter and is one of the brightest stars in the night sky. Betelgeuse is roughly 700 light-years distant and has expanded to a diameter larger than the orbit of Jupiter. Astronomers estimate it will explode as a supernova sometime within the next 100,000 years, though pinpointing the exact moment is impossible. Recent dimming events have sparked speculation, but the star continues its slow evolution toward collapse. When it does finally detonate, Betelgeuse will become visible in daylight and may outshine the full moon for weeks. Until then, it remains a fascinating target for observation, its variability hinting at instabilities deep within. The shoulder of Orion carries the weight of an impending cosmic event. Betelgeuse may one day explode as a supernova visible even in daylight. When a red supergiant like Betelgeuse exhausts its nuclear fuel, the core collapses within seconds, triggering a cataclysmic explosion that briefly rivals an entire galaxy in brightness. At around 700 light-years away, the resulting supernova would appear in Earth's sky as a brilliant star, easily visible during the day. Historical records of supernovae describe events bright enough to read by at night, and Betelgeuse would likely surpass those accounts. The explosion would pose no danger to Earth at that distance, but it would be the most spectacular astronomical event witnessed by modern humanity. Neutrino detectors would register a flood of particles moments before the light arrived. Astronomers eagerly await such an event, which would offer an unprecedented close-up look at stellar death. One day, Orion's shoulder will blaze with unmatched fire. A supernova can briefly outshine an entire galaxy. During the peak of a supernova explosion, the energy released in a few weeks can equal or exceed the total light output of all the hundreds of billions of stars in a typical galaxy. This extraordinary luminosity allows astronomers to detect supernovae in galaxies billions of light-years away. Type Ia supernovae, arising from white dwarf explosions in binary systems, are especially consistent in brightness and serve as standard candles for measuring cosmic distances. Core collapse supernovae from massive stars are more variable, but equally brilliant. Both types seed the universe with heavy elements forged in the explosion or in the seconds before collapse. Without supernovae, the cosmos would lack the raw materials for planets and life. These titanic blasts punctuate the quiet darkness with moments of unparalleled brilliance. The Crab Nebula is the remnant of an explosion witnessed by ancient astronomers. In the year 1054, observers in China, Japan, and the Middle East recorded the sudden appearance of a brilliant guest star visible even in broad daylight. Over time, it faded from view, leaving behind an expanding cloud of glowing debris now known as the Crab Nebula. Located roughly 6,500 light-years away in the constellation Taurus, this remnant continues to grow at a rate of about 1,500 kilometers per second. At its heart lies a pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse. The Crab Nebula has become one of the most studied objects in the sky, providing insights into supernova physics and the behavior of extreme matter. It connects modern astronomy to the observations of stargazers nearly a millennium ago. The guest star of 1054 still speaks to us across the centuries. Pulsars spin with such precision they rival atomic clocks. When a massive star collapses, its core can compress into a neutron star only about 20 kilometers across, yet containing more mass than the Sun. Conservation of angular momentum causes the neutron star to spin extraordinarily fast, sometimes completing hundreds of rotations per second. Magnetic poles emit beams of radio waves that sweep across space like lighthouse beams. From Earth, we detect regular pulses as each beam momentarily points our way. The stability of these pulses is remarkable. Some millisecond pulsars keep time with an accuracy rivaling the best atomic clocks on Earth. Astronomers use them to test theories of gravity and search for gravitational waves. These spinning remnants are nature's most precise timekeepers, ticking steadily across the cosmos. Pulsar timing arrays, networks of these precision beacons, are now employed to detect the faint ripples in space-time caused by merging supermassive black holes in distant galaxies. Magnetars possess magnetic fields trillions of times stronger than Earth's. Magnetars are a rare type of neutron star, with magnetic fields of staggering intensity. While Earth's magnetic field measures a fraction of a Gauss, a magnetar can exceed 100 trillion Gauss, strong enough to distort atoms and create exotic states of matter. These fields decay over time, releasing tremendous bursts of X-rays and gamma rays that can be detected across the galaxy. A magnetar within a few light-years of Earth could pose a genuine threat to life, stripping the atmosphere and disrupting electronics. Fortunately, none are that close. The origin of such extreme magnetism is not fully understood, but likely relates to the turbulent conditions during core collapse. Magnetars demonstrate that the universe routinely produces phenomena far beyond everyday human experience. They are cosmic extremes lurking within the quiet darkness. Only a few dozen magnetars have been identified in our galaxy, making them exceptionally rare compared to ordinary neutron stars and pulsars. Black holes hide in the night sky, revealed only by their effects. Black holes emit no light of their own and are invisible against the backdrop of space. We detect them indirectly through their gravitational influence on nearby matter. When gas spirals into a black hole, it heats to extreme temperatures and emits X-rays that space telescopes can observe. Stars orbiting unseen companions reveal the presence of massive dark objects through their motions. Gravitational lensing, the bending of light from distant sources, can also betray a black hole's location. The first image of a black hole shadow, captured by the Event Horizon Telescope in 2019, confirmed decades of theoretical predictions. Scattered throughout the Milky Way are stellar mass black holes, and at the galactic center, a supermassive behemoth. These invisible giants shape their surroundings while remaining forever hidden. Scientists estimate that our galaxy alone may contain hundreds of millions of stellar mass black holes, the remnants of massive stars that exhausted their nuclear fuel. Some black holes consume nearby stars and flare brightly as they feed. When a star wanders too close to a black hole, tidal forces can shred it apart in a violent event called a tidal disruption. The stellar debris forms a swirling accretion disk around the black hole, heating to millions of degrees and radiating across the electromagnetic spectrum. These flares can outshine entire galaxies for weeks or months before fading. Astronomers detect them in distant galaxies and use them to study the feeding behavior of supermassive black holes. The flares reveal details about the mass and spin of the devouring black hole. Tidal disruptions are rare in any given galaxy, perhaps occurring once every 10 to 100,000 years. When they happen, they provide a dramatic illustration of gravity's destructive power. Feeding black holes briefly announce their presence before returning to darkness. The study of these events has accelerated in recent years, as automated surveys scan the sky nightly for transient phenomena. A supermassive black hole lies at the heart of our galaxy. At the center of the Milky Way, roughly 26,000 light-years from Earth, lurks a black hole containing the mass of about 4 million suns. It is known as Sagittarius A*, named for the constellation in which it appears. Stars near the galactic core orbit this invisible giant at tremendous speeds, their paths traced over decades to confirm its presence. In 2022, the Event Horizon Telescope released an image of the shadow cast by Sagittarius A*, further validating theoretical models. Despite its mass, the black hole currently accretes matter slowly and remains relatively quiet compared to active galactic nuclei in other galaxies. Its influence extends across the inner region of the Milky Way, shaping stellar orbits and ejecting occasional hypervelocity stars. Our galactic heart beats with the gravity of an unseen colossus. Beyond our sight, the night sky holds countless galaxies. Even in regions that appear completely dark to the naked eye, powerful telescopes reveal galaxies by the thousands. Deep field images taken over many hours expose faint smudges of light, each one a distant island of stars containing billions of suns. Current estimates suggest the observable universe holds at least 200 billion galaxies, though improved surveys continue to refine that figure. Most of these galaxies are far too dim to register without long exposures and sensitive instruments. Their combined light contributes to a faint cosmic glow called the extragalactic background. Looking into the darkness between stars is not seeing emptiness but glimpsing the early stages of our instruments' ability to resolve ever fainter objects. The sky is crowded beyond imagination, even where it seems most empty. New infrared surveys are now detecting dwarf galaxies so small and faint that they were previously hidden, expanding the cosmic census to ever smaller and more distant objects. Galaxies come in spirals, ellipses, and chaotic irregular forms. Astronomers classify galaxies into several broad categories based on their shapes. Spiral galaxies like our Milky Way feature sweeping arms wound around a central bulge, often studded with bright star-forming regions. Elliptical galaxies are smooth, featureless ovals containing older, redder stars and relatively little gas and dust. Lenticular galaxies sit between these types, possessing a disk but lacking prominent spiral structure. Irregular galaxies defy neat categorization, their shapes distorted by gravitational interactions or simply lacking symmetry. The classification scheme developed by Edwin Hubble in the early 20th century remains in use today, though refinements continue. Galaxy shape correlates with star formation history, age, and environment. From elegant spirals to chaotic irregulars, the zoo of galaxies displays the diversity of cosmic architecture. Modern surveys have revealed that galaxy morphology can change over cosmic time, with spirals transforming into ellipticals through mergers and collisions. Some galaxies collide and merge in slow cosmic dances. Gravity draws galaxies together over hundreds of millions of years, stretching and distorting their shapes as they interact. Colliding galaxies may pass through one another, their stars rarely colliding despite the crowded appearance. Gas clouds, however, slam together and compress, triggering intense bursts of star formation. Eventually, repeated encounters cause the galaxies to merge into a single larger structure. The Milky Way and Andromeda are on a collision course destined to unite in roughly 4 to 5 billion years. Simulations suggest the merger will transform both spirals into a giant elliptical galaxy. Though violent in appearance, these cosmic collisions unfold so slowly that any inhabitants would notice only gradual changes in their sky over millions of years. Mergers are the architects of large galaxies. Some of the most luminous galaxies known are starburst systems undergoing intense mergers, their gas compressed into furious episodes of stellar birth. The Magellanic Clouds are satellite galaxies visible from the southern hemisphere. Two fuzzy patches adorn the skies of the southern hemisphere, appearing to the naked eye as detached fragments of the Milky Way. These are the large and small Magellanic Clouds, irregular dwarf galaxies gravitationally bound to our own. The large cloud lies roughly 160,000 light-years away, the small cloud slightly farther. Both orbit the Milky Way and have experienced gravitational interactions that triggered star formation and distorted their structures. They are named after the explorer Ferdinand Magellan, whose crew famously noted them during their circumnavigation of the globe. Telescopes reveal rich populations of star clusters, nebulae, and variable stars within these satellite galaxies. The Magellanic Clouds serve as nearby laboratories for studying stellar evolution outside the main body of the Milky Way. A stream of hydrogen gas stretches between the clouds and our galaxy, evidence of their ongoing gravitational interaction with the Milky Way. Star clusters are families of suns bound together by gravity. Scattered across the Milky Way are groups of stars that formed from the same collapsing cloud and remain gravitationally linked. Open clusters like the Pleiades typically contain a few hundred to a few thousand stars and are found within the galactic disk. They are relatively young and gradually disperse over hundreds of millions of years as stellar motions carry members apart. Globular clusters are far denser, appearing as spherical swarms of ancient stars orbiting in the halo surrounding the galaxy. Both types of cluster provide valuable information about stellar ages, distances, and chemical compositions. By comparing stars within a cluster, astronomers can test theories of stellar evolution, because all members share the same age and initial composition. Clusters are stellar families, each telling a story of birth and eventual dispersal. The Hyades cluster, visible near Aldebaran in Taurus, is the closest open cluster to Earth and has been used for centuries to calibrate cosmic distance measurements. Globular clusters can contain hundreds of thousands of ancient stars. Globular clusters are among the oldest structures in the galaxy, with many dating back more than 12 billion years. Their stars formed in a burst of activity during the early universe, when the Milky Way was still taking shape. Today, these dense spherical swarms orbit far from the galactic plane, tracing paths that carry them through the halo. A typical globular cluster may hold between 100,000 and 1,000,000 stars packed into a region only a few dozen light-years across. The crowded cores are so dense that stellar encounters can alter orbits and create exotic binary systems. Omega Centauri and 47 Tucanae are among the most impressive globular clusters visible to naked-eye observers in the southern sky. These ancient relics are time capsules preserving conditions from the earliest epochs of cosmic history. Their low metal content reflects the primordial composition of the universe before generations of supernovae enriched the interstellar medium. Some globular clusters are nearly as old as the universe itself. Age estimates for globular clusters often exceed 12 billion years, placing their formation within the first billion years after the Big Bang. These clusters predate the formation of the Milky Way's disk and record the chemical abundances of the early universe. Because their stars are so ancient, they contain far fewer heavy elements than younger populations like our Sun. Measuring the ages of globular clusters provides an independent check on the age of the cosmos derived from other methods. If clusters were older than the universe, something would be seriously wrong with our models. Fortunately, the ages align, reinforcing the timeline established by cosmic microwave background studies. These venerable swarms are the elders of the stellar community, having witnessed the galaxy grow from infancy. The ages of globular clusters helped constrain the Hubble constant and settle debates about whether the universe is truly 14 billion years old. Meteor showers return every year as Earth crosses comet trails. Comets shed dust and debris as they approach the Sun, leaving trails of particles strewn along their orbits. When Earth's path intersects one of these trails, the particles enter our atmosphere and burn up as meteors. Because the debris follows the comet's orbit, the shower appears to radiate from a fixed point in the sky, giving each shower its name. The Perseids radiate from Perseus, the Leonids from Leo, and so forth. Showers occur around the same dates each year, because our orbit carries us through each debris stream at predictable intervals. Some showers are reliable performers, producing dozens of meteors per hour. Others vary dramatically depending on the density of the stream. Meteor showers are celestial reunions, annual encounters between Earth and the dusty legacies of wandering comets. Observing a meteor shower requires no equipment beyond a clear sky and patience, making it one of the most accessible astronomical events. The Perseid meteor shower in August is among the most celebrated. Each summer, around mid-August, Earth plunges through the debris trail left by Comet Swift-Tuttle, producing one of the most reliable and prolific meteor showers of the year. Under ideal conditions, observers can count 60 to 100 meteors per hour, streaking from the constellation Perseus. The shower's timing coincides with warm northern hemisphere nights, making it a favorite for casual stargazers and seasoned astronomers alike. Perseids often produce bright fireballs and leave glowing trains that linger against the stars. Records of the Perseid shower date back nearly 2,000 years, appearing in Chinese and European historical texts. The shower remains strong because Comet Swift-Tuttle replenishes the debris stream on each return, roughly every 130 years. August nights invite skywatchers to lie under the stars and watch the celestial fireworks. The best viewing typically occurs after midnight, when the radiant rises high in the sky, and observers face directly into the oncoming stream of particles. Ancient records describe brilliant meteor storms filling the night. Historical chronicles from many cultures document extraordinary displays in which meteors fell so rapidly that witnesses struggled to count them. The Leonid meteor shower has produced some of the most famous storms, with rates reaching thousands or even tens of thousands of meteors per hour in peak years. In 1833, a Leonid storm over North America was so intense that people awakened by the spectacle believed the end of the world had come. Similar accounts appear in Chinese, Arabic, and European texts spanning centuries. These storms occur when Earth encounters particularly dense clumps within a comet's debris trail. Most showers do not produce storms, but the potential is always there, lurking in the orbital dynamics of comet dust. Ancient meteor storms remind us that the night sky can suddenly explode with unexpected wonder. The study of historical records helps modern astronomers predict when similar outbursts might occur again. The Geminids are unusual meteors born from an asteroid rather than a comet. Most meteor showers originate from debris shed by comets, but the Geminids trace their ancestry to a strange object called 3200 Phaethon. This body behaves more like an asteroid yet occasionally displays faint cometary activity, earning it the designation of rock comet. The Geminids peak in December and are among the strongest showers of the year, often rivaling or exceeding the Perseids in intensity. Their meteors tend to be slower and less prone to leaving persistent trains, reflecting the denser composition of asteroidal particles compared to cometary fluff. The Geminid shower has grown stronger over the past 2 centuries, as gravitational perturbations have shifted the debris stream closer to Earth's orbit. Understanding why an asteroid-like body sheds so much debris remains an active area of research. The Geminids challenge our understanding of the boundary between asteroids and comets. Fireballs can blaze bright enough to cast shadows at night. Among the many meteors that streak across the sky, a few stand out for their exceptional brilliance. Fireballs are meteors that outshine all the planets, sometimes reaching the brightness of the full moon, or even surpassing it. When a fireball crosses overhead, observers on the ground may notice fleeting shadows dancing as the light source moves rapidly across the dome of the sky. These events typically involve larger particles, perhaps the size of pebbles or even small rocks, entering the atmosphere at high speed. Eyewitness reports often compare the experience to a slow-motion flash of lightning illuminating the landscape. Fireballs can occur at any time, unannounced, catching even veteran skywatchers by surprise. For a few seconds, night briefly retreats as this cosmic intruder blazes its final path. Bolides explode with thunderous sound as they break apart in the atmosphere. Bolides are exceptionally bright fireballs that fragment explosively during their descent. As the object plunges deeper into denser air, the pressure and heat become too great for it to remain intact. The disintegration releases a burst of light and energy, sometimes accompanied by sonic booms that can rattle windows and startle wildlife on the ground. In rare cases, fragments survive to reach the surface as meteorites. The Chelyabinsk event of 2013 demonstrated the power of bolides when a small asteroid exploded over Russia, injuring over 1,000 people, mostly from broken glass. Such events remind us that the boundary between atmosphere and space is not impermeable. Bolides are dramatic punctuation marks in the ongoing story of Earth's bombardment by space debris. Earth is constantly brushed by tiny meteors every single night. Most of the material striking our atmosphere is so small that it burns up completely without producing a visible trace. Scientists estimate that Earth accumulates tens of thousands of tons of cosmic dust each year, delivered grain by grain from comets, asteroids, and interplanetary space. This steady rain of particles is invisible to the naked eye, but can be detected with specialized radar and satellite observations. On any given night, an observer with patience might see a handful of sporadic meteors, unconnected to any organized shower. These are fragments of the random debris littering the solar system. The gentle accumulation of cosmic dust has continued since Earth formed, contributing trace amounts of exotic elements to our planet. We are perpetually bathed in the remnants of the solar system's formation. Some meteors leave glowing trails that linger in the sky. Bright meteors sometimes deposit a streak of ionized gas and vaporized material in their wake that remains visible for several seconds or longer. These persistent trains glow faintly as they dissipate, sometimes twisting and distorting in high-altitude winds. The phenomenon occurs when the meteor's passage heats the surrounding air to incandescence and strips electrons from atoms. Under dark skies, a lingering train can be tracked with the naked eye as it slowly fades and drifts. Occasionally, observers photograph these ghostly remnants to document their evolution. The effect is most common with fast, bright meteors from cometary debris. These fading trails are subtle reminders that even a brief flash can leave a lasting mark on the sky. The moon is our closest and most faithful celestial companion. Orbiting just under 400,000 kilometers away, the moon dominates our night sky with its silvery glow. It is by far the largest object visible to the naked eye after the sun, and has shaped human culture, calendars, and mythology since the dawn of awareness. The moon's gravitational pull stabilizes Earth's axial tilt, contributing to the moderate climate that supports complex life. Its phases have served as timekeepers for planting, harvesting, and religious observance across every civilization. Astronauts have walked on its dusty surface, returning samples that revealed the moon's violent origin from a colossal impact billions of years ago. Yet even after centuries of observation, the moon continues to inspire wonder. Its familiar face is a constant companion, rising and setting through every chapter of human history. Future missions aim to establish permanent bases on the lunar surface, opening a new era of exploration beyond Earth's protective atmosphere. The phases of the moon served as humanity's first calendar. Long before written records, early humans tracked the moon's cycle from new to full and back again, using it to organize their lives. The roughly 29.5-day lunar month became the basis for calendars in cultures spanning every continent. Many words for month derive from terms for moon. reflecting this ancient connection. Agricultural societies timed planting and harvesting by the lunar phases, while religious traditions scheduled ceremonies around full or new moons. The regularity of the cycle provided a reliable clock in an era without mechanical timekeeping. Even today, several calendars, including those used in Islamic and Jewish traditions, follow the moon rather than the sun. The lunar rhythm shaped human consciousness and remains embedded in our languages and rituals. The interplay between lunar and solar cycles led to the development of intercalary months and other adjustments still used in calendrical systems around the world. Lunar eclipses transform the moon into a copper-colored orb. During a total lunar eclipse, the full moon passes entirely into Earth's shadow, where it would disappear completely were it not for our atmosphere. Sunlight bending around Earth's edge is filtered by the air, scattering blue light away and allowing red wavelengths to reach the moon's surface. This scattered light paints the lunar disk in shades of orange, red, and brown, earning the event the popular name blood moon. The exact hue depends on atmospheric conditions, such as dust, volcanic ash, and cloud cover at the time. Unlike solar eclipses, which are visible only from narrow paths, a lunar eclipse can be seen by anyone on the night side of Earth. These events unfold slowly enough for observers to watch the progression from partial to total and back. A lunar eclipse transforms the familiar moon into an eerie apparition glowing faintly in shadow. Many ancient cultures feared the blood moon as a celestial omen. When the familiar silver disk turned rusty red without warning, early peoples often interpreted the event as a sign of divine anger or impending disaster. Myths from Mesopotamia warned of eclipses as attacks by demons, while Chinese folklore described a dragon swallowing the moon. Similar fears appear in the records of Greek, Roman, and Mesoamerican civilizations. Rituals were performed to drive away the threat, including loud noises, chants, and offerings. Over time, observers began to notice that eclipses followed predictable cycles, allowing priest astronomers to forecast them and relieve public anxiety. This transition from fear to understanding marked a significant step in the development of scientific thinking. The blood moon's ominous reputation lingers in folklore, even as modern science has stripped it of supernatural meaning. A total lunar eclipse can last for more than an hour. Unlike solar eclipses, which reach totality for only a few minutes at most, the totality of a lunar eclipse can stretch well over an hour. The longest lunar eclipses occur when the moon passes through the center of Earth's shadow, at a time when the shadow is at its widest. The entire event, including partial phases before and after totality, can span several hours, giving observers ample opportunity to watch the progression. The moon's slow journey through the shadow allows even casual viewers to appreciate the color changes and gradual dimming. Photographers capture the blood-red moon with relative ease, compared to the fleeting moments of a total solar eclipse. These unhurried events invite contemplation, turning the sky into a slow-motion theater. A long lunar eclipse is a rare gift of extended cosmic wonder. Solar eclipses sweep across Earth with a racing shadow. When the moon passes between Earth and the Sun, its shadow traces a narrow path across our planet's surface. Within this path, observers witness the Sun blotted out entirely for a few precious minutes. The shadow moves at well over 1,000 kilometers per hour, racing from west to east as the moon's orbit carries it forward. Outside the path, viewers see only a partial eclipse, the moon covering a varying fraction of the solar disk. The spectacle of totality, during which the Sun's corona blazes around the dark lunar silhouette, draws thousands of eclipse chasers to remote locations around the globe. Solar eclipses occur somewhere on Earth roughly twice a year, but any given spot may wait centuries between passes. The speed and rarity of totality make each occurrence a memorable event. During totality, stars emerge in the daytime sky. In the minutes when the sun is entirely hidden by the moon, the sky around the eclipsed sun darkens to a deep twilight blue. Bright stars and planets that normally cannot compete with daylight suddenly appear near the blacked-out disk. Observers often report a sudden drop in temperature and a hush that falls over wildlife confused by the sudden onset of pseudo-night. The sun's corona, normally invisible against the brilliant solar surface, fans out in delicate streamers and loops. This brief glimpse of the inner solar atmosphere is a major focus of scientific study. The appearance of stars during the day is a haunting reminder of how thin the barrier between day and night truly is. For those few minutes, the universe feels tangibly close. Ancient astronomers could predict eclipses with surprising accuracy. Centuries before modern science, Babylonian, Chinese, and Greek scholars recognized that eclipses follow recurring cycles. The Saros cycle, roughly 18 years and 11 days, repeats nearly identical eclipses because the Sun, Moon, and Earth return to almost the same relative positions. Using carefully maintained records spanning generations, priest astronomers could anticipate when the next eclipse would occur and prepare their communities accordingly. This predictive power enhanced their status and often tied astronomical knowledge to religious authority. The ability to forecast what seemed like divine intervention marked an early triumph of empirical observation over superstition. These ancient efforts laid the groundwork for later developments in celestial mechanics. Millennia ago, the first eclipse predictors took humanity's initial steps toward understanding the clockwork of the heavens. Venus shines so brightly it can cast faint shadows on the ground. Venus is the third brightest natural object in our sky after the Sun and Moon. At its peak brilliance, it can reach an apparent magnitude of nearly -5, bright enough to produce faint shadows on snow or white surfaces under the right conditions. Its dazzling appearance results from its thick reflective clouds of sulfuric acid, which bounce sunlight efficiently back into space. Venus appears as either the evening star or the morning star, never straying far from the Sun in our sky because its orbit lies inside Earth's. Ancient observers sometimes mistook the two apparitions for separate celestial bodies. The planet's radiance has inspired countless myths and poems across human history. On clear nights, Venus commands attention even in areas affected by moderate light pollution. Beneath its bright clouds lies a hellish surface where temperatures exceed 400 degrees Celsius and atmospheric pressure crushes like the deep ocean. Jupiter gleams steadily, outshining most stars in the heavens. With an apparent magnitude often exceeding -2, Jupiter is typically the second brightest planet in the night sky after Venus. Unlike stars which twinkle due to atmospheric disturbance, Jupiter's disk is large enough to smooth out those fluctuations, making it appear steady and serene. Its brightness comes from reflecting sunlight off cloud tops, composed primarily of ammonia ice crystals. Jupiter reaches opposition roughly every 13 months, when it appears directly opposite the Sun and shines at its brightest. During these periods, it dominates the midnight sky and is easily visible from urban locations. Binoculars reveal its 4 largest moons as tiny points of light, while even modest telescopes show cloud bands and the famous Great Red Spot. Jupiter's commanding presence has fascinated stargazers since antiquity. The planet's immense gravity has shaped the solar system, deflecting comets and asteroids that might otherwise have struck the inner planets more frequently. With simple binoculars, Jupiter's moons appear as tiny jewels. Galileo first observed the 4 largest moons of Jupiter in 1610, using a telescope of modest power by modern standards. Today, ordinary binoculars can replicate that observation, revealing Io, Europa, Ganymede, and Callisto as faint points strung out beside the planet. Night after night, their positions change as they trace orbits around Jupiter, a motion visible over just a few hours of careful watching. These 4 satellites are among the most intriguing objects in the solar system, hosting volcanoes, subsurface oceans, and ancient cratered surfaces. Observing them is a direct connection to the moment astronomy transformed into a science of discovery rather than mere cataloging. Anyone with binoculars and a steady viewing position can share Galileo's thrill of finding new worlds. The moons of Jupiter await patient eyes on any clear night. Saturn's rings can be glimpsed through even a small telescope. No other site in the solar system quite compares to Saturn's iconic ring system. A telescope with a magnification of around 50 times or more will reveal the rings as a distinct extension of the planet's disk. The site has astonished observers for centuries, from the first blurry images recorded by Galileo to the crisp photographs returned by modern spacecraft. The rings consist of countless particles of ice and rock, ranging from grains to house-sized boulders, orbiting in a flat plane around the planet. Their appearance changes over Saturn's nearly 30-year orbit as the rings tilt toward or away from Earth. At certain angles, they seem to disappear entirely because they are so thin relative to their width. Saturn remains a favorite target for amateur astronomers, offering a view of celestial grandeur accessible to anyone with a modest telescope. The Cassini spacecraft revealed intricate structures within the rings, including waves, gaps, and moonlets that shepherd particles into distinct bands. Mars sometimes glows brighter than Jupiter with its ruddy light. Every 2 years or so, Earth overtakes Mars on its inside track, bringing the red planet closer than usual and causing it to flare in brightness. At opposition, Mars can outshine every star in the sky and rival Jupiter in luminosity. Its distinctive orange-red color, caused by iron oxide dust covering its surface, makes it unmistakable against the starry background. Ancient observers associated the planet with war and blood, leading to its naming after the Roman god of battle. The brightness varies considerably from one opposition to the next, because Mars's elliptical orbit brings it closer to Earth at some oppositions than others. During the closest approaches, telescopic observers can glimpse polar ice caps and dark surface markings. Mars remains a focus of both scientific exploration and human imagination. Robotic rovers and landers have explored its craters and valleys, returning images that reveal a world with ancient riverbeds and the potential for past life. Mercury is elusive, hiding near the Sun's glare. Mercury's orbit keeps it close to the Sun from our viewpoint, never straying more than about 28 degrees away. This means the planet is only visible low on the horizon, shortly before sunrise or after sunset, and only during favorable elongations. Thick haze near the horizon and the brightness of twilight often mask it from casual observers. Ancient astronomers struggled to observe Mercury reliably, and some may never have seen it at all. Those who do catch it are rewarded with a faint, rapidly flickering point of light dancing in the atmospheric turbulence. Observing Mercury requires careful attention to timing and a clear view of the horizon. Despite being one of the 5 classical planets visible to the naked eye, it remains the most challenging to spot. Uranus and Neptune can barely be spotted under pristine dark skies. Uranus hovers at the edge of naked eye visibility, appearing as a faint point of light at about magnitude 6 under truly dark and clear conditions. Neptune lies beyond unaided vision, requiring binoculars or a telescope to detect. Both planets were unknown in antiquity because their dim glow blended with background stars. Uranus was discovered in 1781 by William Herschel, and Neptune followed in 1846 after its position was predicted mathematically. Even with optical aid, neither planet shows obvious features to small telescopes. Their disks appear as tiny colored dots. Uranus has a subtle blue-green tint, while Neptune is a deeper sapphire blue. Observing them is a quiet triumph of persistence and patience. They remind us how much lies beyond the reach of the naked eye. Comets occasionally streak the night sky with glowing tails. Comets are icy bodies that spend most of their lives in the frozen outer reaches of the solar system. When one falls inward toward the Sun, heat vaporizes its ices, releasing gas and dust that stream outward to form a brilliant tail. The tail always points away from the Sun, pushed by solar wind and radiation pressure, so a comet's tail can precede or follow its head, depending on its direction of travel. Great comets, visible to the naked eye and spanning large stretches of sky, are rare but memorable events. Historical records describe comets appearing as omens before significant events, though the timing was coincidental. Modern astronomy has revealed comets as pristine samples of the solar system's primordial material. When one graces our sky, it offers a glimpse of ancient ice thawing in the light of our Sun. Comets often display two distinct tails, a bluish ion tail driven by magnetic forces, and a yellowish dust tail curved by gravity. Some comets return only after thousands of years away. Long-period comets have orbits so vast that they may spend tens of thousands or even millions of years traversing the outer solar system before reappearing near the Sun. When one of these distant wanderers finally swings close, it often arrives unannounced, discovered by astronomers only weeks or months before perihelion. Because they approach the Sun so infrequently, these comets retain more volatile ices, sometimes producing spectacular displays of outgassing. Their orbits can be perturbed by the gravitational influence of passing stars and galactic tides, occasionally sending new comets sunward for the first time in human memory. Once they round the Sun, they retreat back into the dark, not to return within any recorded history. These visitors from the deep freeze carry material unchanged since the solar system's earliest days. Each appearance is a once-in-civilization event. Halley's Comet visits roughly once every 76 years. Perhaps the most famous of all periodic comets, Halley's Comet has been recorded by observers for over 2 millennia. Its orbit takes it from beyond Neptune's distance to inside Earth's orbit, completing the journey approximately every 76 years. Historical accounts likely include sightings dating back to at least 240 BCE, and the comet appears in the Bayeux Tapestry commemorating events of 1066. Edmund Halley was the first to recognize that several past apparitions were the same object, predicting its return and earning the comet its name. Each visit brings renewed public excitement and scientific study. The next perihelion passage is expected in 2061, when a new generation will witness this celestial traveler. Halley's Comet is a thread connecting centuries of human observation. Spacecraft have visited the comet during its recent approaches, revealing a dark, peanut-shaped nucleus venting jets of gas and dust into the vacuum of space. For centuries, comets were feared as omens of disaster. Before their nature was understood, comets appeared without warning and hung in the sky for weeks, their ghostly tails stretching across the heavens. This unpredictability made them objects of dread, interpreted as signs of war, plague, or the death of rulers. Chronicles from ancient Rome, medieval Europe, and imperial China abound with accounts linking comet apparitions to misfortune. The word disaster itself derives from Latin roots, meaning bad star. As astronomy advanced, observers recognized comets as natural bodies following predictable orbits, stripping them of supernatural significance. Yet echoes of the old fear persist in popular culture and fiction. The transition from omen to object of study mirrors humanity's broader journey from superstition towards scientific understanding. Some comets have crumbled apart in full view of Earth. Not all comets survive their close encounters with the Sun intact. The stresses of heating, outgassing, and gravitational forces can fragment a comet nucleus, producing chains of smaller pieces that drift apart over time. In 1994, comet Shoemaker-Levy 9 famously broke into fragments before plunging into Jupiter, giving astronomers an unprecedented view of planetary impacts. Other comets have simply fizzled as they approached perihelion, never living up to early brightness predictions. Observers have watched comets split into multiple pieces, each developing its own faint tail. These disintegrations provide valuable data about the internal structure and composition of comet nuclei. A dying comet's final performance offers science a glimpse of its hidden interior. Auroras drape the polar skies in shimmering curtains of light. The aurora borealis in the north and aurora australis in the south are among nature's most breathtaking displays. Glowing curtains of green, pink, violet, and red ripple across the sky, shifting and dancing in response to invisible forces. The phenomenon occurs when charged particles from the Sun interact with gases in Earth's upper atmosphere, exciting atoms and causing them to emit light. The colors depend on the type of gas and the altitude of the interaction. Green is most common, produced by oxygen at moderate altitudes, while red and violet come from higher oxygen and nitrogen respectively. Indigenous cultures around the Arctic Circle wove auroras into mythology, seeing spirits, ancestors, or celestial fires. Modern travelers journey to high latitudes, hoping to witness the spectacle firsthand. Time-lapse photography has captured the rapid motion of auroral displays, revealing how quickly the curtains shift and pulse in response to changing solar wind conditions. Auroras form when solar wind strikes Earth's atmosphere. The Sun continuously emits a stream of charged particles called the solar wind. When this wind encounters Earth's magnetic field, most particles are deflected, but some spiral along field lines toward the poles. Upon entering the atmosphere, they collide with oxygen and nitrogen molecules, transferring energy that is re-emitted as light. During periods of heightened solar activity such as solar storms and coronal mass ejections, the auroras intensify and can be visible at lower latitudes than usual. Historical records describe auroras seen as far south as the Caribbean during major geomagnetic storms. The interplay between solar activity and Earth's magnetosphere creates a dynamic light show that varies from night to night. Each auroral display is a reminder of the invisible forces linking our planet to the Sun. Scientists monitor space weather closely to predict when aurora-producing events will sweep past Earth, giving enthusiasts advance warning to prepare for potential displays. In the far north, auroras can appear almost every night. Residents of high-latitude regions such as northern Scandinavia, Alaska, and northern Canada often enjoy frequent auroral displays during the darker months. When the Sun is active, the probability rises further, and observers can witness shows ranging from faint glows to intense pulsating curtains filling the entire sky. Long winter nights and minimal light pollution make these areas prime destinations for aurora tourism. Dedicated websites and apps now provide forecasts based on solar activity and geomagnetic indices, helping enthusiasts plan their observations. Locals may grow accustomed to the lights, but visitors frequently describe the experience as life-changing. The northern lights transform ordinary nights into unforgettable spectacles of cosmic energy. In some indigenous traditions, the lights are believed to be messages from ancestors or the footsteps of the departed walking across the heavens. Auroras also shimmer above other planets in our solar system. Earth is not unique in hosting auroral displays. Any world with a magnetic field and an atmosphere can generate auroras when struck by the solar wind. Jupiter boasts auroras far more powerful than Earth's, fueled in part by charged particles from its volcanic moon Io. Saturn, Uranus, and Neptune also exhibit polar lights, captured by spacecraft and space telescopes. Even Mars, with its patchy remnant magnetic field, produces localized auroras in regions where crustal magnetism persists. Studying auroras on other planets helps scientists understand the interactions between stellar winds and planetary magnetospheres. These alien light shows expand our perspective on a phenomenon we once thought belonged solely to our own skies. The zodiac constellations once guided farmers in planting and harvesting. Along the path the sun appears to travel across the sky, a belt of 12 constellations became known as the zodiac. Early agricultural societies noticed that certain constellations rose before dawn at specific times of year, providing cues for when to plant, irrigate, or harvest crops. The appearance of Taurus might signal spring planting in one region, while Scorpius heralded the approach of autumn elsewhere. These associations were practical rather than mystical, arising from generations of observation. Over time, astrology intertwined the zodiac with personality and fate, but its origins lie in the rhythms of the farming year. The constellations served as a calendar written across the night sky. Today, their agricultural role has faded, replaced by precise calendars and weather forecasts. The ecliptic marks the sun's yearly path through the sky. As Earth orbits the sun appears to move against the background of stars, tracing a great circle called the ecliptic. This imaginary line passes through the 12 zodiac constellations and defines the plane of our solar system. The Moon and major planets also follow paths close to the ecliptic because they orbit in nearly the same plane. Ancient astronomers charted the ecliptic carefully, using it to predict planetary positions and eclipses with remarkable accuracy. The name itself derives from the Greek word for eclipse, reflecting the fact that eclipses occur when the moon crosses this line. Understanding the ecliptic was a foundational step in the development of celestial mechanics. The sun's highway across the heavens anchors our understanding of planetary motion. Precession slowly shifts the positions of stars over millennia. Earth's axis does not point in a fixed direction, but wobbles in a cycle lasting roughly 26,000 years. This precession causes the celestial poles to trace circles across the sky and shifts the positions where stars appear relative to our seasons. The effect was noticed by the Greek astronomer Hipparchus over 2,000 years ago, when he compared his observations to older records. Because of precession, the constellation that rose with the sun at the spring equinox has changed over time, moving backward through the zodiac. The slow drift also explains why Polaris was not always the North Star, and will not remain so forever. Precession is a subtle dance between Earth and the cosmos, invisible on human timescales but profound over the ages. The night sky looked different when dinosaurs roamed the Earth. Mesozoic skies, stretching from over 200 million to 66 million years ago, displayed constellations unrecognizable to modern observers. The proper motion of stars, combined with precession and stellar evolution, has rearranged the heavens completely. Stars that burned brightly then have faded or exploded, while new suns have ignited and drifted into prominence. The Sun itself has circled the galactic center multiple times since the age of the dinosaurs, passing through different stellar neighborhoods. The familiar patterns we call the Big Dipper and Orion are temporary arrangements that did not exist in the past and will not persist into the deep future. Each era inherits a fresh canvas of lights. The sky above the dinosaurs was theirs alone, as ours belongs to us. Some stars move so swiftly they distort constellations over time. While most stars appear fixed on human timescales, a few possess proper motions large enough to be detected within a few decades of observation. These high-velocity stars shift noticeably against the backdrop, slowly undoing the patterns we recognize. Over thousands of years, even moderate proper motions accumulate, reshaping constellations into new forms. Astronomers measure proper motion in arcseconds per year, a tiny angle but significant when multiplied by millennia. Future generations will inherit a sky subtly different from ours, with familiar asterisms stretched and bent by stellar journeys. The constellations are not eternal murals, but passing configurations in an ever-changing gallery. The stars move quietly, reshaping the heavens while we sleep. Barnard's star drifts faster across the sky than nearly any other. Located just under 6 light-years away, Barnard's star is a dim red dwarf invisible to the naked eye, but famous among astronomers for its exceptional proper motion. It shifts about 10 arcseconds per year, meaning that over the course of a few centuries, its position has changed noticeably against background stars. In roughly 10,000 years, it will have moved the apparent width of the full moon across the sky. Despite its speed, it is still so far away that the motion is imperceptible without precise measurements. Barnard's star has been the subject of investigations for possible planetary companions, though confirmed planets remain elusive. Its rapid journey through our neighborhood makes it a fascinating case study of stellar kinematics. This modest red dwarf holds the record for the fastest apparent motion known. Satellites drift like artificial stars across the night sky. Since the launch of Sputnik in 1957, thousands of satellites have joined the natural objects orbiting Earth. Many of these are visible to the naked eye as steady points of light gliding smoothly across the heavens, typically from west to east. Unlike meteors, which streak and vanish in an instant, satellites move at a measured pace, taking several minutes to cross from horizon to horizon. Their brightness depends on size, altitude, and the angle at which sunlight reflects off their surfaces. Dedicated websites and smartphone apps allow observers to track satellites in real time, predicting when and where each will appear. Satellite watching has become a popular pastime, combining the wonder of space exploration with the accessibility of a clear night. The stars now share the sky with our mechanical creations. The International Space Station often outshines all but the Moon. Orbiting roughly 400 kilometers above Earth, the International Space Station reflects sunlight brilliantly, sometimes reaching an apparent magnitude of -6. This makes it brighter than Venus, and visible even from urban areas with significant light pollution. When conditions are right, the station appears as a fast-moving, non-blinking point, traversing the sky in a few minutes. Observers can sometimes spot it passing in front of the Moon or Sun, a phenomenon called a transit. The ISS has hosted rotating crews of astronauts since 2000, conducting research in microgravity. Watching it pass overhead connects viewers to the human presence in orbit, a reminder that spacecraft with people aboard are circling overhead right now. The station is among the most observed artificial objects in history. satellite flares can briefly rival Venus in brightness. Certain satellites produce sudden flashes known as flares, when sunlight glints off highly reflective surfaces, such as solar panels or antennas. The Iridium communications satellites were famous for producing predictable flares, bright enough to attract attention even during twilight. These events last only a few seconds, during which the satellite can outshine every star and planet in the sky. With the replacement of the original Iridium constellation, such dramatic flares have become rarer, but other satellites still produce occasional glints. Observers sometimes mistake satellite flares for meteors or aircraft lights until they notice the steady glide across the sky. Predicting flares adds an element of anticipation to satellite watching. A well-timed flash is a fleeting moment of brilliance among the stars. Rockets sometimes paint glowing trails across the upper atmosphere. When rockets vent excess fuel or perform maneuvers in the upper atmosphere, they can create luminous clouds visible from the ground. These exhaust plumes spread and twist in the thin air high above, catching sunlight and glowing with soft colors. The spectacle is most dramatic when launches occur near dawn or dusk, allowing the exhaust to be illuminated while the lower sky remains dark. Social media often buzzes with images of these unusual formations, sometimes mistaken for otherworldly phenomena. High-altitude venting from spacecraft can produce spirals, arcs, and shimmering curtains, unlike anything natural. These transient artworks are byproducts of humanity's ventures into space. Rocket twilight phenomena remind us of the increasing overlap between Earth's atmosphere and the realm of human exploration. The night sky has grown busier with human-made lights in orbit. The number of active satellites has surged in recent years, driven by mega constellations designed to provide global internet coverage. Thousands of small satellites now circle the planet, appearing as trains of lights shortly after launch before gradually dispersing into individual points. Astronomers have raised concerns about the impact on observations, as bright satellites can spoil long-exposure images and interfere with scientific surveys. Efforts are underway to reduce reflectivity through experimental coatings and adjusted orientations. Meanwhile, casual observers may find the increased traffic both fascinating and bittersweet. The night sky that inspired myths and guided navigators now bears the marks of our technological ambitions. Balancing access to space with the preservation of dark skies is an emerging challenge for the 21st century. The Hubble Space Telescope revealed breathtaking views of deep space. Launched in 1990, the Hubble Space Telescope orbits above the distorting effects of Earth's atmosphere, capturing images of unprecedented clarity and depth. Its observations have transformed our understanding of the cosmos, from measuring the expansion rate of the universe to imaging protoplanetary disks around young stars. Iconic photographs such as the Pillars of Creation in the Eagle Nebula and the Hubble Deep Field have become cultural touchstones, bringing the beauty of space into public consciousness. Hubble continues to operate decades beyond its original mission, periodically serviced by astronauts during the shuttle era. Its data archive remains a treasure trove for researchers worldwide. The telescope demonstrated that placing instruments above the atmosphere opens windows onto the universe previously closed. Hubble's legacy endures in both science and inspiration. Every patch of darkness hides a multitude of unseen galaxies. When astronomers point powerful telescopes at seemingly empty regions of sky, long exposures reveal galaxies by the thousands where none were visible before. These faint smudges of light are distant island universes, each containing billions of stars and spanning tens of thousands of light years. The deeper the exposure, the more galaxies appear, suggesting that no part of the sky is truly empty. This finding revolutionized our understanding of cosmic structure, revealing a universe far more densely populated than earlier estimates suggested. The darkness between stars is merely an optical illusion imposed by distance and the limits of our instruments. Every blank canvas awaits the patience and sensitivity to unveil its hidden contents. The night sky is not empty. It is simply waiting to be seen. The Hubble Deep Field uncovered thousands of galaxies in a tiny speck of sky. In 1995, the Hubble Space Telescope stared at a nearly blank patch of sky for 10 consecutive days, accumulating light from the faintest and most distant objects it could detect. The resulting image, known as the Hubble Deep Field, revealed roughly 3,000 galaxies in an area of sky smaller than a grain of sand held at arm's length. Many of these galaxies existed when the universe was less than 1 billion years old. Subsequent deep field observations using improved cameras uncovered even more, pushing the count into the tens of thousands. These images fundamentally changed how humanity perceives the scale of the cosmos. They demonstrated that galaxies stretch back to the visible edge of the universe, and perhaps beyond. A tiny dot of sky became a window into cosmic history. Time itself flows differently across the cosmos. Einstein's theories of relativity revealed that time is not absolute but varies depending on speed and gravitational strength. Near massive objects, time passes more slowly compared to regions far from gravity's grip. Astronauts aboard the International Space Station age slightly less than people on the ground because of their relative speed and weaker gravitational influence. Near a black hole, time would grind nearly to a halt from an outside observer's perspective. These effects, though tiny in everyday life, have been measured with atomic clocks and must be accounted for in satellite navigation systems. The fabric of time is woven into the geometry of space itself. Looking out at the night sky, we observe objects existing in different temporal frames, a mosaic of moments frozen at various points in cosmic history. Every star in the night sky is a glimpse into the past. Because light travels at a finite speed, every object we observe appears as it was when the light left it, not as it exists now. A star 500 light-years away is seen as it looked 500 years ago. The Sun appears as it was 8 minutes in the past. The most distant galaxies visible through our telescopes appear as they were billions of years ago, when the universe was young and turbulent. This cosmic time delay means astronomy is inherently historical, a science of ancient light arriving at our instruments. We cannot see the present state of the universe, we can only reconstruct it from echoes of the past. Every glance upward is an act of looking backward through time. Some starlight began its journey before humans even existed. The light reaching us tonight from the most distant visible stars left its source millions of years ago, traveling across the void long before the first anatomically modern humans walked the Earth. Stars in the halo of our own galaxy can lie tens of thousands of light-years away, meaning their light started outward when mammoths roamed and ice ages gripped the planet. Some objects visible through modest telescopes emit light that departed during the age of dinosaurs. The photons entering your eyes tonight may have been born in nuclear furnaces that have since exploded into supernovae, leaving only remnants. We observe a frozen record of stellar evolution, a gallery of moments preserved across deep time. The night sky is not merely a spectacle, it is an archive written in ancient light. The cosmic microwave background is the afterglow of creation itself. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms, allowing light to travel freely for the first time. That initial flash of photons has been traveling ever since, stretched by the expansion of the universe into microwave radiation that permeates all of space. Detected accidentally in 1965, the cosmic microwave background confirmed the Big Bang theory and provided a snapshot of the infant cosmos. Its tiny temperature fluctuations map the seeds of all future galaxies and the large-scale structure we observe today. Precise measurements of this relic radiation have shaped modern cosmology, revealing the age, composition, and geometry of the universe. The afterglow surrounds us in every direction, a faint whisper from the dawn of time. This ancient radiation permeates every corner of space. The cosmic microwave background fills the universe uniformly, arriving from all directions with remarkable consistency. Its temperature averages about 2.7 kelvins, just a few degrees above absolute zero, yet varies by minute amounts that scientists measure with extraordinary precision. Satellites such as COBE, WMAP, and Planck have mapped these variations in exquisite detail, uncovering information about the universe's density, expansion rate, and contents. The patterns imprinted in this radiation reveal the geometry of the cosmos and support the concept of cosmic inflation. Although invisible to the naked eye, this faint glow represents the oldest light we can ever observe. Beyond it lies an opaque curtain of plasma that blocks our view of earlier epochs. The cosmic microwave background is the horizon of visibility in time. The earliest galaxies formed during the cosmic dawn. A few 100 million years after the Big Bang, the first stars ignited and began gathering into proto-galaxies, initiating an era astronomers call cosmic dawn. These early structures were smaller and more chaotic than the grand spiral and elliptical galaxies we see today. Over billions of years, collisions and mergers assembled them into the larger galaxies populating the modern universe. Understanding this formative period is a major goal of contemporary astrophysics, as it explains how light and heavy elements spread throughout space. The transition from darkness to starlight reshaped the universe's chemistry and thermal state. Observing these distant epochs requires powerful telescopes sensitive to infrared light stretched from ancient ultraviolet emissions. The story of cosmic dawn is the story of how structure arose from smoothness. The James Webb Space Telescope peers back toward that distant dawn. Launched in late 2021, the James Webb Space Telescope is the largest and most powerful space observatory ever deployed. Its 6.5-meter gold-coated mirror collects infrared light with unprecedented sensitivity, enabling it to observe the earliest galaxies that formed after the Big Bang. Within its first year of operation, Webb shattered records for detecting the most distant known objects, revealing galaxies that existed when the universe was only a few 100 million years old. Its infrared vision can penetrate dust clouds to see star-forming regions hidden from optical telescopes. Webb's observations are rewriting textbooks on stellar birth, planetary atmospheres, and cosmic history. The telescope operates from a point beyond the Moon, shielded from the Sun's warmth and Earth's glow. A new era of discovery has begun. Some stars orbit the galactic center at dizzying speeds. Stars near the supermassive black hole at the heart of the Milky Way travel along elliptical paths at velocities reaching thousands of kilometers per second. One such star, known as S2, completes an orbit in about 16 years, skimming within 20 billion kilometers of the black hole at its closest approach. Observing these stars, provided key evidence for the existence of Sagittarius A*, the 4 million solar mass black hole at the galactic center. Their rapid motions allowed astronomers to weigh the invisible mass lurking there with remarkable precision. The extreme gravitational environment tests Einstein's general relativity under conditions impossible to replicate on Earth. Despite their violent surroundings, these stars survive, tracing out cosmic dances around an unseen partner. Their orbits map the curvature of space itself. Hypervelocity stars are flung outward like cosmic slingshot stones. Some stars travel through the galaxy at speeds far exceeding the typical orbital velocities, propelled by gravitational encounters with the central supermassive black hole. When a binary star system strays too close to Sagittarius A*, one star can be captured while its companion is hurled outward at velocities of more than 1,000 kilometers per second. These hypervelocity stars race through the halo and may eventually escape the Milky Way altogether. Detected first in 2005, they serve as probes of the galactic potential and the mass distribution of the dark matter halo. Their trajectories allow astronomers to trace paths back to the galactic center, confirming their violent origin. Hypervelocity stars remind us that gravity can act as both a trap and a catapult. The galaxy continuously sheds a few of its citizens into intergalactic space. Rogue planets wander invisibly through the darkness without any sun. Not all planets orbit stars. Some drift through interstellar space alone, ejected during the chaotic formation of planetary systems, or gravitationally stripped by passing stars. These rogue worlds receive no sunlight and are therefore extremely difficult to detect, revealing themselves only through brief gravitational lensing events when they pass in front of distant stars. Estimates suggest that rogue planets may outnumber stars in the Milky Way, representing a hidden population wandering unseen in the darkness. Some may retain thick atmospheres or subsurface oceans, heated by residual internal warmth, raising intriguing questions about habitability. Their discovery challenges traditional definitions of planetary systems and expands the environments where exoplanets exist. The night sky conceals countless orphan worlds drifting silently through the void. Vast clouds of dust obscure entire regions of the galaxy from view. Interstellar dust consists of tiny grains of carbon and silicates, ejected by dying stars and dispersed by stellar winds. These particles absorb and scatter visible light, blocking our view of distant stars and the galactic center. The dark lane running through the Milky Way in summer skies is a visual testament to these obscuring clouds. Without alternative wavelengths of light, entire stellar populations and star-forming regions would remain hidden from optical telescopes. The dust also plays a crucial role in chemistry, providing surfaces where molecules form and eventually contributing to planetary building blocks. What appears as darkness in the sky may actually be teeming with activity veiled behind cosmic curtains. Understanding dust distribution is essential for interpreting the structure of our galaxy. Infrared light can pierce these clouds to reveal hidden suns. While visible light is blocked by interstellar dust, infrared radiation passes through more easily, allowing astronomers to peer into regions otherwise inaccessible. Infrared telescopes reveal newborn stars still wrapped in their natal cocoons, and the crowded stellar populations near the galactic center. Observations from space, such as those by the Spitzer Space Telescope, and now the James Webb Space Telescope, have opened infrared windows onto the cosmos. These instruments detect the warmth of objects too cool to shine in visible light, including brown dwarfs and protoplanetary disks. Infrared astronomy has revolutionized our understanding of star formation and the distribution of matter in galaxies. By shifting to longer wavelengths, scientists convert darkness into insight. The hidden universe emerges when observed in the right light. Radio waves from quasars travel across billions of years to reach us. Quasars are the luminous cores of distant galaxies powered by supermassive black holes devouring surrounding material. They emit radiation across the electromagnetic spectrum, including powerful radio waves that can traverse billions of light years to be detected by radio telescopes on Earth. The first quasars discovered appeared star-like in optical images, but radiated far more energy than ordinary stars. Their extreme distances and brightness made them key tools for probing the early universe and the intervening material along the line of sight. Radio observations of quasars helped establish the cosmic distance scale and revealed the large-scale structure of the universe. These signals carry information from epochs when galaxies were forming and merging at high rates. Quasars are beacons illuminating the history of cosmic evolution. Some quasars blaze brighter than entire galaxies combined. Although quasars occupy regions no larger than our solar system, they can outshine the combined light of hundreds of billions of stars in their host galaxies. This extraordinary luminosity arises from the immense gravitational energy released as matter spirals into the central supermassive black hole. The accretion disk surrounding the black hole heats to millions of degrees, radiating intensely across all wavelengths. Some quasars are visible across more than half the observable universe, serving as distant lighthouses for studying cosmic expansion. Their brightness allows astronomers to detect absorption features from intergalactic gas along the line of sight. Quasars illuminate not only the universe around them, but also the invisible material between us and their distant glow. Nature's brightest engines reside in the hearts of galaxies. Gamma-ray bursts shine for moments yet outshine the entire universe. For fractions of a second to several minutes, gamma-ray bursts release more energy than the Sun will emit over its entire 10 billion-year lifetime. These cataclysmic events occur when massive stars collapse into black holes, or when neutron stars collide, focusing jets of high-energy radiation into narrow beams. If such a burst occurred nearby and pointed toward Earth, the consequences for the biosphere could be severe. Detected first by military satellites in the 1960s, gamma-ray bursts remained mysterious until space observatories pinpointed their distant origins. They occur randomly across the sky, providing extreme laboratories for testing physics under conditions impossible to replicate. Although brief, their afterglows linger, as expanding fireballs that fade over days to weeks. Gamma-ray bursts mark the most energetic events since the Big Bang. The night sky is alive with signals across the electromagnetic spectrum. Beyond the visible light that reaches our eyes, the cosmos radiates in radio waves, microwaves, infrared, ultraviolet, X-rays and gamma rays. Each wavelength reveals different phenomena. Radio telescopes detect pulsars and cold gas, infrared probes, dust-shrouded stars, ultraviolet highlights hot young stars, and X-rays illuminate accretion disks around black holes. Specialized observatories, many orbiting above Earth's absorbing atmosphere, capture these invisible signatures and translate them into images we can understand. Multi-wavelength astronomy builds a comprehensive picture by combining data across the spectrum. What appears dark or static in one band often blazes in another. The night sky is not merely a gallery of visible points. It is a symphony playing on countless frequencies beyond human perception. Every glance upward is a look into the history of the universe. The finite speed of light transforms the night sky into a living museum, where objects at varying distances appear at corresponding moments in cosmic history. Nearby planets reveal their current state, while distant quasars display conditions from billions of years ago. Astronomers sift through these layers of time to reconstruct the evolution of stars, galaxies, and the universe itself. This natural time machine allows us to witness stellar births and deaths, galaxy collisions, and the gradual development of cosmic structure. The deeper we look, the further back we see, approaching the limits of visibility imposed by the expansion of space. Every photon reaching our instruments carries a fragment of the past, encoded in its wavelength and intensity. The night sky is both a window and a history book. The sky has carried countless generations and will carry countless more. From the earliest humans who tracked the seasons by the stars, to modern astronomers probing distant galaxies, the night sky has been a constant companion to every civilization. It inspired mythology, guided navigation, and sparked scientific revolutions that reshaped our understanding of existence. Future generations will look upward as we do, even as the constellations slowly shift and new stars emerge from interstellar clouds. The sky remains a shared heritage connecting past, present, and future across the vast sweep of time. Light years above, the same nuclear furnaces burn, indifferent to the rise and fall of empires below. The questions we ask of the heavens are the same questions our ancestors posed. Where did we come from, and what lies beyond? The night sky endures, an eternal source of wonder and discovery. And now the quiet wonders of the night sky begin to gently fade into the stillness of sleep. You have wandered through over 100 peaceful truths about the heavens above. From the familiar glow of the moon to galaxies hidden in what looks like empty darkness. From shooting stars blazing across the atmosphere to pulsars spinning faster than thought. From ancient constellations that guided sailors across unknown oceans to the faint afterglow of creation itself, still warming the cosmos after nearly 14 billion years. You have explored how light travels across unimaginable distances, how time bends near massive objects, and how the atoms in your very body were forged inside stars that lived and died long before our sun was born. You have learned that the night sky is not merely a canopy of distant lights, but a living archive of cosmic history, carrying stories older than language itself. You are connected to this story more deeply than you may realize. Right now, as you listen, starlight is still streaming toward Earth from every direction. Ancient photons that began their journey millions or billions of years ago are arriving at this very moment. The same light that once bathed dinosaurs, the same glow that shone upon the first humans who looked up in wonder. It continues, patient and eternal. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the slow turning of the constellations across the heavens. Like the quiet pulse of distant pulsars keeping time across the galaxy. Tonight as you rest, the universe continues its ancient work. Stars will burn, galaxies will turn. Meteors will streak silently across the sky above you. Comets will drift in the outer darkness, waiting for their return. And somewhere, light from an event that happened before Earth even existed, is just now arriving, carrying a message from the deep past. You are a small, warm presence beneath this vast celestial expanse. peacefully resting among the wonders. Sleep well. Sweet dreams. And may you carry with you the quiet knowledge that the same stars watching over you tonight have watched over every dreamer who ever lived, and will continue their silent vigil long after we are gone. Thank you for joining me on this journey through the wonders of the night sky. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the cosmos and the mysteries that surround us. There are more wonders waiting. More secrets hidden among the stars. More gentle truths to drift through on quiet evenings. Rest well. And may the soft light of distant suns keep you company through the night. This has been Drowsy Discovery. Good night.